Okay, I'll make a start. Welcome everyone to this IES webinar, Combustion Transition, a simple framework for accelerating our transition to net zero. This webinar has been organised to coincide with the energy theme day at COP27 this year and is part of a wider programme of IES activities during COP27. We're really pleased today to be joined by Simon Spooner. Simon is an environmental scientist working for Atkins consultants in the UK. He specialises in developing and applying mathematical models combined with social, political and regulatory methods to plan and design better infrastructure systems and improved environmental conditions. As ever, after Simon's presentation, you'll have the opportunity to ask questions, so please do submit these in the Q&A function at the bottom of your screen at any point during the presentation, and I will then ask these out on your behalf later on. This webinar is also being recorded and will be made available on the IES YouTube channel. Thanks so much for logging in today. Simon, over to you.
Great, thank you, Ethny. Yeah, it was a pleasure to be here today, and I have a topic to talk on which very special to me, something I've been trying to develop over the last few years, which I think could be quite helpful in considering our current situation. So this is basically all about fire. And the point is that fire is a great thing. It seems obvious, we take it for granted, but it really is behind the wealth of modern civilization. We have learned to control fire, first few twigs and bits of wood, but now fossil fuels and immense power and energy that comes from that. And the effect on our society and our species has been dramatic. This here shows growth in population over the last couple of hundred years, absolutely massive, and also the proportion of people living in poverty. It's around sort of mid-20th century that the use of combustion systems became really widespread around the world, and you can see the impact that that has had. Of leading to more people living wealthy lives. Obviously, there are still poor people around, and some of that may be in danger of getting worse unless we get on top of our situation. But it has been a very positive thing for us. But we need to understand, where does fire come from? We take it for granted. We think it's sort of a fundamental, well, that's how things are. But actually, it's not. Fire is very closely linked to the force of life itself. And life, so we don't actually know what it is. We know when things are living, we know when they're not, but we're not quite sure what it is. But before life came along, there would have been no fire on Earth. Fire only comes from living things, because it's living organisms that separate the oxygen and the reduced matter of carbon and other things to create this sort of disequilibrium. And once that had been running along for quite a long time, took a long time to happen, about 500 million years ago, you reached a point there was enough oxygen in the atmosphere to support fire. So some bit of dried out moss got hit by a bolt of lightning or something, and the first fire started. The mark of life is disequilibrium. Fire is a return to equilibrium. It's like the sort of death in a way. But ancient life has also left us a treasure of this power, the oxygen in the atmosphere, which is built up, and also reduced hydrocarbons buried in the ground. And a lot of them built up in the last few 100 million years. Right now, we are burning through all of that treasure in just a few decades because, it's convenient, it's nice, our species flourishes as a result of it. But at least as we are burning all this treasure, we are building new treasures. We're building our infrastructure, and we're also building knowledge. These are things which last, maybe not for millions of years, but at least for a reasonable length of time, beyond the time that we've burnt the resource. Also, there are alternatives to fire and combustion to give us all those things that we want. So, what are we doing now? We know the world is burning, and we are talking about carbon, greenhouse gases, climate, all these things. Yes, those are very important, and we've got to deal with them, but actually they are the symptoms and not the cause of the problem. The cause of the problem is the combustion that we're addicted to using, and that is so convenient for us. So thinking about our energy systems, got some nice figures from Our World in Data and IEA and places, and you can look at really what's going on over the years with all that oil. Like that population, you saw that population took off in 1950, so did our energy use. Most of that energy use is fossil fuels, a bit of wood and biomass as well. 93% of all of that energy use is combustion. 86% of it fossil fuels, say some is wood and biomass. And that is responsible for somewhere between 70 and 80% of our greenhouse gas emissions. I'm getting increasingly vague on that because I think evidence is growing for land use having a bigger influence than maybe we used to think. But nonetheless, combustion chambers are the absolute main thing. And why do we use them? Well, they give us money, wealth, they're valuable. We really make use of them. They also produce noise, air pollution. Most of that's coming from there, resource depletion, and a lot of social inequality and this consumptive burning economic system. But as I say, there are alternatives. Most of that circles around electricity. Some can also be mitigated combustion, where you start dealing with the negative impacts when you still need to use that process. And of course, there's always reducing the amount that we consume and using less energy. So those are the sort of three directions that have to be taken on. And I'm going to sort of focus more on the electricity side of that. And, worldwide, on the electricity, our energy use, 80% of it is direct combustion and about 20% is electricity. Now, of course, most of that electricity is produced by combustion. So it's still, in many parts of the world, it's all produced by combustion. But that is the sort of balance that we are looking at. So what are we going to do about this? The thing to bear in mind, the real problem, it's not the big power stations, it's millions and millions of small combustion chambers that we use. The boiler in the cupboard in our house, the engine in our car, the little motors in industry and things. These are what produce most of the emissions and sort of, the different processes. Most of these are very inefficient, especially internal combustion engines, absolutely terrible. By contrast, those great big power stations, those are actually very efficient combustion processes. Those can actually be the best places to burn it. If you're going to burn stuff, that's a good place to burn it. So what we've got to do is we've got to transition to non-combustion systems, mostly electricity, or to using sort of carbon capture storage to deal with the combustion. And we need to do this by addressing it sector by sector, because the processes, the routes, they're quite different in different areas, and we need to break that down into the industries. But there is some good news in this transition. These electrical systems, which they are much, much more efficient than the combustion systems generally. So they can give you the same car service for a lot less energy. So if you've got an electric vehicle, you can drive around to the same places and use about a third of the total energy that you would using an internal combustion. And that's assuming that you're getting that initial energy from a gas power station. If you are just getting it from renewables, even more efficient. So that's a great way that we can get the same services and use less energy. And the same in heating systems. When you use heat pumps, you can reduce your energy consumption by a half or even to a fifth of what's required for a gas boiler. So there is hope on the way ahead. So as I said, combustion, it's our addiction to combustion that is the main cause of the problems. And this is my sort of manifesto of this, few key points. So to recount, combustion, 80% of greenhouse gases, 93% of energy use. It's in the combustion that fossil fuels are realized for their economic value. And this is an important point. Fossil fuels in themselves, we're not interested. I mean, you might, use them for a few niche uses and a face cream or something, but it's not until you burn them that you really get the value. and it's the people burning them that are adding that value. So also a combustion chamber is always a component of other infrastructure, and it provides services that are of value to individuals and society. Electricity is only a small part of it at the moment, 20% of energy use. So we've got to look at all of combustion, not just power stations and the so-called energy industry. The great thing is that every combustion chamber is owned by somebody. They get value from it. They can be held responsible for the cause of the problem at that point. And at that point is an easy place to manage, because combustion is a closed process. You count what goes in and you can count what comes out, and you know who's responsible for it. So what we need to do is to develop the incentives, economic measures that change those behaviors and investment decisions, change what combustion systems you buy, how to transition to using non-combustion alternatives, or to deal with them at that point, not thinking just about carbon or GHG in general. I'm just going to run through a few sort of observations about this transition as well. One is efficiency makes transition easier. It's not an end. If you insulate your house, you've not solved the problem, because you've still got a gas boiler in there. You might be using a third less energy or half the energy, but you're still emitting those greenhouse gases. If you switch to a heat pump in your house, you are now having zero emissions, whether you've insulated it or not. It's just that if you insulate it, maybe you need a smaller heat pump. It's easier to run. And obviously you've shifted the problem somewhere else, but it can be more easily dealt with in that place. A post-combustion civilization, and once we're there, it will still be high energy intensity, and you can still have economic growth. It's not all about stopping things, but the main limit will probably be the availability of materials. We need to build a vast amount of new infrastructure, and we need materials to do that. And energy can be, with renewables and nuclear, we can produce a lot of energy. We can replace the fossil fuels. We can give something else, but we need this infrastructure. We need the materials to make it. And to get those materials, we do have to emphasize the amount of circular economy, focus on keeping that material flow around, which uses more energy. So there are some sort of hurdles to overcome. Also, in those materials, as you turn things into, combustion is embodied in materials. So steel, cement, these effectively embody a lot of combustion in them. So a bit like embodied carbon, you can think of it in the same way. It also means that if you remove the combustion processes from the delivery of those, you are reducing your impact in that way. So reducing the embodied combustion increases your sustainability. There's another aspect of this, going back to the bit about life, the rather philosophical stuff, that it's actually life processes create this disequilibrium. And so part of the transition we have to make is also not just stopping burning stuff, but helping life to recreate that disequilibrium, reverse that process. And that means changing the way that we use our land, releasing more of that land back to nature. But we still got to eat, and we use most of our land for food. So it probably means, more high intensity, more energy intensive areas of some land, and then sort of diverse systems elsewhere. So we need to sort of change the way that we manage the land, give a bit more space to nature, and that can sort of have regenerative capacity. So I now want to talk about, I'll come back to that bit a bit later maybe, but anyway, I now want to talk about how we work on that transition. So first of all, we've got to think combustion transition is transition. It's not just thinking about the sunlit uplands of where we want to be in our post-combustion society, but how do we get there? What are the stages that we have to go through, and how do we decarbonize all our different industries? And we need to focus on giving the services without the damage. And also, I think very much to phase it out from the point of demand. So think about where you are using that combustion process, those small millions of small units, and go back up the system, not top down from how do I supply lots of electricity, but how do I change my combustion process to an electrical one. That will create the demand for electricity, and that will be supplied. The economics will supply where there's demand. you've got to do this in stages, and you've got to maintain resilience as you're going. You need backups, and you've got to have a sort of transition plan. So how do we plan this? We want this plan. What do we use to plan for? First of all, we've got two metrics that I've developed based on these ideas for doing that. The first one is this non-combustion metric. This is basically, where are we? How far do we have to go to reach our goal of non-combustion? And the second is, okay, for the combustion processes you've got, how efficient are these? What's their impact? And this is the combustion accounting measure. So first of all, I will introduce a little bit more about the non-combustion measure, about the amount of energy and how much of that is non-combustion. I will slightly strangely give examples from Oman, from the Sultanate of Oman. This is because the first job that I had actually applying combustion transition theory was for our preparation of the Oman National Spatial Strategy, which was a project that Atkins did for the Sultanate of Oman to develop their development plan till 2040. And in that plan, their headline metric for their environmental plan is the non-combustion transition metric. So the percentage of total energy demand which is met from non-combustion based processes. And this is just some gumph about how that is incorporated into their policy system. And it is national policy in Oman. Don't think they understand all the implications of it, but they've gone for it. And it's actually very interesting from a petrostate point of view, but that's another discussion. Anyway, how do we come up with this metric? One of the ways of looking at it, it's very simple. You can just take the basic data from IEA and things. And this is sort of showing for the Sultanate of Oman, their energy use over the last 30 years or so, and what they use it in the different sectors which use the energy. And for that energy, you can see what are the different sources of that energy. You can see that about 16% of their energy use is from electricity. And then of that electricity, that's the amount of electricity which is used in each sector. And then that electricity is actually only about 1% non-combustion. So there you have the sort of energy use in the different sectors, and how much of that is electrical. And you can work out the percentage of electricity, very simple thing. But I give this the fancy name as a non-combustion metric, because this is basically how much of what are you doing is not using combustion. And then when you're planning, you can start thinking about setting targets for your non-combustion. Where do we want to get to in our plan to 2040? And then you can start to do a few calcs and some numbers here, but you can see, well, where am I at the moment? Yeah, at the moment, only 2% of electricity is non-combustion. 15% of their demand side was non-combustion. So their compound energy system non-combustion is 0.3% of all of Oman's energy use is non-combustion, which is not great. They have got an ambitious plan by 2040 to get to 62% renewables. I don't think they're going for nuclear yet. And then if they could up their demand side use, then to also get to 60%, then they would be at 37% non-combustion. This would be an absolutely massive effort and achievement, and you're not even 40% of the way to where you want to be to. They would also have to increase their electricity generation from 34 terawatt hours to about 128. So it's quite a big change. So that was Oman. Let's look at the same sort of process for the good old UK. So we've got that same sort of what's used in each sector. We about 21% electrical, and this is how much of electricity is used in each sector. And this gives us that same table. We're actually slightly bigger numbers than Oman, so we're around 1,400 terawatt hours a year of total energy use, 300 or so electric. And we can have some similar sort of targets for our system, but let's say we're going to achieve these by 2030 maybe. And you can do that same analysis. So at present, we work out at about 9.3% non-combustion. And sorry, and the UK, that's with 40. We think we're 43.5% of the way there on our electricity production. All that wind and renewables and nuclear and everything, but actually we're only about 9% of where we need to be. So if we were by 2030 to achieve 85% non-combustion electrical generation, and we were to go from 21% to 60% on our demand side, we will get ourselves to 51%. And we would also have to increase our electrical production. But let's start unpacking that a little bit as well. So, how do you make that transition? Well, I'll just come on to that second metric, which is the combustion accounting one. So this is about looking at the actual combustion processes individually. And that's saying, well, basically, you take your energy source, a barrel of oil or a puff of gas, and you put that in a combustion chamber, bang, it does some work. So that's a percentage efficiency conversion there from the energy that went in to the useful energy that comes out. That generates your value. That's why you do it. On the sides, you've got your greenhouse gas emissions and you've got air pollution, which could be measured in terms of sort of health impacts and things, which is a very serious problem. And you've also got resource depletion. So you can count those. But the main thing is like this efficiency of how much it's converted. You could then weight that by these other sort of purple elements if you want to get into a bit more detail, and you can go into sort of natural capital accounting and things with this as well. But that's just giving a basic overview of this metric. Now we'll look at how you might apply it. So here we've got the greenhouse gas emissions for the UK, just downloaded from the government's website earlier. And you can see what the main sources are. So transport, 27%, our energy systems, all the power generation, that's 21%, and business and residential, these are, there are some slight issues in industry and things also comes into this, but that's a lot. There's slightly different ways of counting things in the UK. And I'm trying to compare this with the sort of data that comes from the IEA. And here I'm just selecting, not looking at the agriculture and things, but we are looking at in the inside here is the total energy use by different sectors. So industry, transport, residential, and then commerce and public. And on the outside here is the amount of electricity that we're using in each of these sectors. And you can see some features here, such as transport, tiny use of electricity because we run around in gas and diesel cars. Industry and commerce and public, they have a reasonable amount of they're actually quite a large amount of electrical use because you've got a lot of factories and things, they use electricity to drive those processes. And the commerce and public, that's a mixture of buildings, but also water treatment, utility services and things, all of which consume a lot of electricity, and then residential as well. Now, the total amount of electricity, it is only 21% of that in a number. Maybe it should be the other way around, but this is how I've got them. And these are our non-combustion metrics around the edge here. 45%, we're using quite a lot of electricity in that. Fair amount in industry, very little in transport. Then these explosion ones, these are our combustion accounting metrics. These are a couple of estimates for it. And this is basically saying, well, in a residential thing, you're normally using gas boilers and the like. And a gas boiler, an old one turns about 70% of the energy in the gas into useful heat. And a really good modern condensing boiler maybe will get 90% of the energy that's coming out of the pipe into heat where you want it, with a really good distribution system. So that's sort of the typical kind of range of performance. Transport systems, very poor efficiency. By the time you've taken oil, refined it, got it into a petrol tank, burnt it, and gone through everything, only about 15 to 20% of the energy that you started off with is turned into actual useful motion, kinetic energy of moving about. Some things get a little bit more efficient, but typically it's pretty low. So there's lots of gains to be had there. Then you can think, well, how do I start to apply these things? Where do I go? I had those objectives of getting to 60% or different targets. And what does that, how does that affect our planning of our energy use, our future transition? So I've narrowed in on some specific numbers for our combustion accounting. So I'm going to say, well, residential boilers are 80%, cars are 20% rather than a range. And I've got some very approximate figures for industry. The problem is different sectors will be wildly different. Some will be highly efficient, some will be less so. So we've got those. And then in combination with the expected move towards non-combustion systems, also you can look at how that efficiency will improve. Because say for residential systems, if you move to heat pumps, you're looking at 200 to 500% efficiency. Yeah, it's more than, because for each kilowatt hour that you use to run your heat pump, you might get 3 to 4 kilowatt hours of heat. So there's a big improvement potentially in the efficiency there. So that's a big move forward. And in transport, electric cars are many times more efficient than combustion engine cars, even if you're taking that from a gas power station. So there's huge potential for gain there. Commerce and public, a lot of that's electrical already, so it's a little harder to gain. And in industry, there are a lot of barriers, and some of that's going to have to be done with carbon capture storage type things for high temperature processes. So you can get this transition, and this can help you to know that your total energy use, this is assuming no economic growth by whatever this horizon, it could be 2030, it could be any horizon, assuming no economic growth, but on a like-for-like basis, your total energy use will drop by nearly 400 terawatt hours, but your electrical generation would be nearly 2 times what it is now. So you've got to move ahead with that. So now I want to think about some of these, how you make this transition happen. And I said we've got millions of combustion chambers that need to change throughout that demand side. So how are you going to make that happen? And this is a concept called combustion transition funding, which I'll come on to. So you've got to influence the people who are designing those combustion systems, buying them, using them, and buying the products from them, those which have that sort of embodied combustion in them. And you need to develop economic instruments to influence their decisions, so that they will invest in non-combustion systems. And this is a concept of combustion transition funds. The idea of these is they're new financial instruments that will incentivize change. And they will apply at both the capital stage, when you buy or sell, and at the operational, when you use it. In its crudest form, you could call it you could apply a sort of a tax. Instead of a carbon tax, you put a levy on the combustion process, and you do it on its sort of capacity or the amount of energy it uses. And then you could weight that by the efficiency of that combustion system, and whatever mitigations you can weight it by the level of pollution and greenhouse gas emissions and things. And you can compare that with switching to an electrical or a mitigated combustion system. Now, that levy, or it could be funds put into an area by government to stimulate change, that goes into a fund which will be sector specific. So say for boiler manufacturers, or for light car industry, or heavy van industry, or heavy goods vehicles, or aviation, or different sectors. But the idea is they have a fund, and that is largely led by that industry. And then people can withdraw from that initially for research and development into non-combustion alternatives, especially where they are there, or for supply chain strengthening to make those alternatives come in. So, to strengthen the sort of battery, electric motor, rare earths manufacturing that you need, and alloys that you need for that sort of thing, to get your supply chain in place. You can also do that for transition measures, some of the mitigation, carbon capture, emissions reduction things, which will affect the weightings that you apply to things. And then ultimately, as that goes on, you would subsidize the substitution with the non-combustion alternatives. So the idea is that these would complement carbon taxes. They start off quite small and grow. The thing with carbon taxes, they work on open processes. They're sort of a global approach with a trickle-down impact. These are focused on the closed process. So it's very, very specific. You start small and you grow up from there. So it's grow up, not trickle down. You're driving that responsibility down to those people who are actually qualified to make that change. And this is the sort of idea of trying to lay out how that can sort of work, that you've got the money side of it. It could be levies, it can be investors investing into things, or it can be government grants. You get this fund that goes for research and development, efficiencies, mitigation, supply chain relevant, and then ultimately market measures and subsidies to skew the market towards the non-combustion systems. And the outcome is your non-combustion infrastructure. You could also have regenerative land use and water use. You could have a certain amount of offsetting in that area, and the development of natural capital to manage some of that aspect. So coming to time now. So to summarize where we've got to. The idea of combustion transition is a framework for analysis, and it focuses on combustion, acknowledging that this is a closed process with an owner that provides valued services and quantified impacts. You need to look at how you change that process sector by sector through manufacturers, owners, users. You can develop these metrics to measure that transition, non-combustion, mitigation, also priority of transition and efficiency, and look at different things. You can consider how efficiency savings, when I say efficiency savings here, I'm saying in the transition to non-combustion, you can have less total energy use. That can lower running costs, and also because you've got far less in terms of negative externalities and costs of impacts. And most non-combustion systems, combustion is a very, very abrasive process. Things wear out and break down very quickly. Whereas a lot of non-combustion systems will need far less maintenance, will be longer living, and once they're in place, they will just keep producing value. It will need to see massive increases in electrical production and supply. And this is where I maybe start to come up with a sort of a counter narrative, because a lot of the focus on net zero is about big polluting fossil power stations and changing our energy supply. I said that's only a small part of the problem at the moment. And also on combustion transition, these are the most efficient combustion processes we have. So my counter narrative is actually, don't worry about it, keep them for now. We need that electricity supply. Put all your effort into changing the demand side. And once you've got your demand side and you can keep supplying that, then gradually phase out the supply side, because you only have to do a very simple calculation which shows you how much greater the advantage is in your transition by doing that. So, focus on that demand side, put out millions of little fires ahead of those few big ones. And then sort of propose these economic, social measures that encourage this change throughout society. And you need to mobilize that capital, think about how you can make that work. But it should work because you've got a reduction in those external costs. There may be bigger expenditures up front, but your long-term returns of a non-combustion system are going to be much more positive and make you more wealthy. So, more you focus on that combustion chamber. The fact is, you get rid of the combustion chambers, you replace them with something else, job done. You don't need to account for carbon. You don't need to do anything else. You've solved the problem. Obviously, that's not easy. So you've got to think about how you get to that point. But it's just a different way of looking at that. And then you can, I'm water sector, so there are things you can look at in the water sector as well. But I shall save that as an extra. So that is what I had to say. I hope it makes some sense, and I'm really keen to have any questions on that.
Thank you very much, Simon, for that thought-provoking presentation. Really interesting. And yeah, all the attendees, please do put your questions in the Q&A function at the bottom of your screen. I'll kick off now. We've already got one in there. So how will resilience be factored into this? Our district network operators are extremely fragile, and with the increasing likelihood of severe or more frequent storms, power outages will likely be more frequent. This could result in severe consequences regarding domestic, commercial, and industrial energy demand. Will adaptation and transition from combustion go hand in hand?
Well, I think that's a very apt question, and this is part of my thing is actually don't get rid of all the combustion in such a hurry. Do think very carefully before phasing out your gas power station. I mean, coal power stations really are pretty bad. The sooner we can get rid of them, the better. But combined cycle gas turbine, 60% conversion of chemical energy to electrical energy. It's super efficient. So, maybe change the emphasis. The emphasis should be on getting rid of all those small combustion systems throughout our infrastructure. That will increase the load on the system. But a lot of these, if these are battery electric, the usual, the classic thing, if you can start connecting some of those batteries into the grid, that can start to balance some of this instability. And having the more things which go electric, also you can have a lot more control over demand. So, heat pump heating systems in residential areas, you can have smart meter links that relate to the grid, and you can have aspects of the amount of heating that goes in maybe managed together with the grid, because sometimes if there's a spike in demand, well, let's just turn down the heating a little bit for a while and then turn it up. So there are a lot of ways in which such a system can be more manageable. This comes into the whole smart grid area that comes in, will become much, much more important.
Great, thank you, Simon. And do you think something like lithium is likely to become a new limiter of economic growth, for example, for its use in EV batteries? Are we well placed to understand the sustainability implications of shifting away from fossil fuels to new, potentially equally non-renewable materials, limiters of economic growth, whatever they happen to be?
Well, as I said, I think those materials are potentially the greatest limitation to what we're doing. Fears of those limitations should definitely not stop us from moving ahead full speed. Certainly with regard to lithium, because with regard to lithium, I say lithium is actually one of the most abundant elements in the earth. There's loads and loads of it around. It's just that it's mostly rather spread out and locked into hard crystalline rocks where it's difficult to get out of, and there's only a few places where it's easy to get at. But there are new processes coming out and it can be obtained. Also, there are alternative battery technologies available. I mean, using lithium ion for grid level storage does seem a bit nuts. I mean, we should probably focus on other things. There are aluminium ion batteries are a potential technology. There are lots of things which can be done. Where I would be careful, the one that I do see as very limiting is platinum group metals. So, for a lot of the hydrogen economy solutions and hydrogen cells and things, a lot of them are reliant on platinum group metals, and there are literally, a few hundred tons of them in the entire earth. So we've got to be a bit careful before going down a route that's dependent on something like that. Other ones, lots of rare earths which are required. Well, most of them aren't as rare as the name suggests. And I think we really need to diversify our supplies for that. So much is coming from China at the moment. It's great that China are doing that for us, but it does leave us a bit vulnerable. And it's a little unfair to put all of the burden of the pollution and the negative impacts of that on one country, and that should be shared a little bit more widely.
Okay, thank you. And in terms of the combustion transition, the combustion levy that you mentioned, and you said it needs to be done in a kind of sector by sector context. But how do you think this would work in the residential environment? So do you see it as the users paying the combustion levy, or how would you see this working?
In the residential environment, yeah, I think initially you would focus on the supply side, on the boiler manufacturers, because what you really want to incentivize, it's totally unfair to hit the users at the moment, because they really don't have an alternative. Yeah, I mean, it's just not there. So the idea of this would at the moment would be you put a small levy on all of the boilers which are sold, and that goes into stimulating through both R&D and through supply chain development for heat pump development, so that we can get more efficient air source, water source, ground source heat pump systems in place. On the residential side, it's another entire discussion, which I've got some following slides, but we won't have time for. I think we need to be using heat networks and using water actually as a medium for moving heat energy around our urban areas and working that in a much more efficient way. But that is another talk, really. But there is a lot that can be done there, and we need to stimulate the supply chain, the R&D and supply chain, to have those heat networks, which maybe can really deliver the solution to, in the UK, where we've got a lot of old buildings which you're never going to get insulated to a very high level. So we've got to make that transition that way.
Great, thank you. And do you think nuclear power is a viable part of the solution, given the potential dangers, decommissioning, water use, etc.? And if it isn't used, will this lead to a massive 20% gap in supply?
I have great difficulty in seeing how you could make this work without nuclear. We want our electrical supply to be non-combustion. Well, we've got a reliability issue with the renewables. They come and they go. And without a base load of nuclear, we're never going to make it. It's also why I think it's important to keep a certain amount of combustion for probably quite a long time in order to balance that supply. It's much more important that we build the supply than we get rid of the combustion in that supply. But I think nuclear is an absolutely vital part of that. The waste issues are a lot better dealt than they used to be. This is not a hopeless problem. Decommissioning, well, we don't want to have spread out too many sites. That is an unpleasant reality, but it's not a complete barrier. Water use, we've seen that in France over the summer, where greatly curtailed the amount that they could use of nuclear they could generate, because they didn't have the cooling capacity. Fortunately, in the UK, we generally build our power stations by the sea, because we've got lots of sea. But it is an important consideration that it is better to put them in coastal locations where you're not going to have that problem.
Great, thank you. And I think we've got time for just one more question. So we've got one from an attendee here who says that they currently work with a rail company who lease out diesel locomotives. So they're not responsible for the operation of the asset. How would you recommend them engaging with their supply chain to reduce embodied carbon emissions of their locomotives? And how can this combustion transition be applied to the rail industry in general? Okay,
so the main application of combustion transition in the rail industry is electrification, go non-combustion. That's what you want to aim for. I understand that there is still a requirement for diesel locomotives because not all those lines are overhead cabled, especially for freight. And maybe this is one of the rare cases where hydrogen is a solution. Generally, I'm not a great enthusiast for hydrogen. It's so inefficient to produce. And, in ordinary vehicles or even goods vehicles, it's just so bulky that it's difficult to work. But a train can deal with a bulky hydrogen tank. There may be safety issues around it that would have to be dealt with, but that is a potential way forward. But it's basically electrification and possibly hydrogen where that's not possible. The other element is the sourcing of the materials from which your locomotives are constructed. And this is also, about motivation towards having low carbon steel. The Swedish are moving towards using hydrogen in steel production. You can use electrolytic processes. They are pretty difficult. Okay, needs a lot more research and development. We need to be maybe putting the combustion levy on current coal steel works in order to fund that transition towards low carbon steel. And this can give a metric which you can apply to work out how to do that. Then as the locomotive manufacturer, you can say, well, our equipment has lower embodied carbon because we're supplying this, and we can have a set of metrics to quantify and calculate exactly what that degree is.
Okay, well, thank you so much, Simon, for presenting today. It was such an interesting topic, and hopefully we'll hear more about it in the future. So thank you for joining us today. And thank you to all our attendees for watching and asking lots of questions. That's always great. So our next IES webinar is tomorrow, and this is focused on Biodiversity Day at COP27. And we'll be holding a webinar on the Kent Wildlife Trust's approach to integrating nature-based solution finance in delivering nature recovery. And you can register for this on the IES website. Thanks very much, everyone. Have a great rest of your day.
Thank you. Bye-bye.